Hello there. Today we are going to solve a linear programming problem. But before we look at the problem, we will first look at the structure of an LP model or a linear programming model. Now, the different parts of the LP model. Number one is the decision variables. Now, variables which are changeable and going to impact the decision function. Like the profit function is affected by both sales and price. Now, which of these two is changeable will be our decision variables. So first, you know the linear programming model has decision variables. Okay, decision variables are those whose values is going to impact the objective function. Now, your objective function could be to maximize revenue or maximize profit or minimize cost. Now, how are you going to maximize profit? Say by producing product A and product B. So in this case, the more the more you produce products A and B, the more the profit will be maximized. So in this case, your product A and product B are your decision variables. So number one is that there are decision variables. Number two is that there's an objective function like I've already mentioned. Okay, now either to maximize or minimize, like maximize profit, sales, production, etc., and minimize cost or loss or energy consumption, wastage, etc. And then you have constraints. Now constraints is is nothing but limitation. Any kind of limitation or scarcity explained through a function like limitations of raw material, time, funds, equipments, etc. All right, these are all constraints. Okay, for example, you want to produce as much as possible. You want to produce product A and product B, but then let's say there are constraints in terms of, let's say, raw material, in terms of machine hours. All right, so you have to achieve your objective function within the limitations, within the constraints. And all remember that you have non-negative constraints. Okay, that your decision variables, for example product A and product B, cannot be -1, -2, -3. It can be 0 or it has to be positive. So your decision variables A, B, X, Y, Z, these are all non-negative constraints. They cannot be -1 or -2. All right, now, so then the next part is formulation of an LP problem. Now you can solve a linear programming problem, an LP problem, using graphical method or using simplex method. But before you could solve a linear programming problem, you have to formulate it first. Okay, so number one is that you have to recognize the decision variables and assign symbols to them like X, Y, Z, and so on. Okay, now these are the quantities we wish to find out. Okay, for example, how much of product A, how much of product B we need to produce. Then number two is express all the constraints in terms of inequalities in relation to the decision variables. Number three, formulate the objective function in terms of the decision variables. And four is add the non-negativity condition or constraints. So let us before we solve the LP problem, let us first formulate it. Now here we have an LP problem. Okay, a firm produces two types of products, P1 and P2, and sells them at a price of rupees 2 and rupees 3 respectively. Each product passes through two machines, M1 and M2. P1 requires 1 minute of processing time on M1 and 2 minutes on M2. P2 requires 1 minute on machine M1 and 1 minute on M2. The machine M1 is available for not more than 6 hours, while machine M2 is available for 10 hours during any working day. The firm wishes to determine its daily product mix so as to maximize revenue. Formulate the above as a linear programming problem and solve it using the graphical method. So you have this problem where where the objective function is to maximize revenue. Okay, how will you maximize revenue? By producing more of these two products, product 1, P1 and P2. Now P1 and P2 are the decision variables. All right, and and decision variables will will change. Okay, now you let us first express these two decision variables. uh, let's say let x and y be the two products P1 and P2 respectively. So there we have already identified the two decision variables, and we've also expressed these two decision variables. Now, how many decision variables can be there? As many as possible. But in this problem, there are only two decision variables, but there can be three or four or even more than three decision variables. All right, and there can be more than one constraint or two constraints, three constraints. There can be multiple constraints. Okay, but in this problem, we're only going to deal with two decision variables. Now, the objective function. So there are two decision variables, and there has to be an objective function. And what is the objective function here? To maximize revenue, right? Say maximize Z. Okay, how will you maximize revenue? By producing X and Y, right? You produce X and Y and sell them, right? You're going to produce product X and Y and sell them. Now, at what price are you going to sell them? See, it's given here, and sell them at a price of ₹2 and ₹3 respectively. So you're going to sell X for ₹2 and Y for ₹3. So there you have the objective function, subject to the constraints. Subject to the constraints. Now there are two constraints here. All right. Number one is, see here, each product passes through two machines M1 and M2. P1 requires 1 minute of processing time on M1 and 2 minutes on M2. P requires 1 minute on machine M1 and 1 minute on M2. The machine M1 is available for not more than 6 hours, while machine M2 is available for 10 hours during any working day. So what are the the constraints the constraints here are basically machine hours. So you have machine hours M1, okay, and machine hours M2. All right, now it says here that the machine M1 is available for not more than 6 hours. So therefore there cannot be, you cannot run M1 for more than 6 hours. Now convert that hours to minutes, because everything is given in minutes. P1 requires 1 minute processing time on M1 and 2 minutes on M2. So convert this hours to minutes. So 6 hours will be, if you convert that to minutes, it will be 360. All right, so machine M2 is available for 10 hours. So convert that to minutes, it'll be 600 minutes. All right, 10 hours is 600 minutes. So these are the two constraints. All right, and it says here that P1 requires, what is P1? P1 is X, requires 1 minute, okay, of processing time on M1. Okay, 1 minute, and 2 minutes on M2, and 2 minutes 2x on M2. All right, and P2 requires 1 minute on machine M1, 1 minute 1x, oh sorry, not x, y, sorry, because P2 is y. P2 requires 1 minute on machine M1, so 1y on M1 and 1 minute on M2, and 1 minute on M2. and these two, cannot exceed 360 minutes. Okay, all right. The total time taken by these two, okay, on machine 1 cannot exceed 360 minutes. All right, it should be equal to or less than 360 minutes. And here also the total time taken by x and y cannot exceed 600 minutes in M2. Okay, and x is greater than 0, and y is also greater or equal to 0. These are non-negative constraints. That the value of x or y cannot be negative. They can be equal to 0, but they cannot be less than 0. All right, these are non-negativity constraints. So there you have it. This is this is how we formulate an LP problem. Now if you're given a problem where you have to formulate, where they ask you to formulate a linear programming problem, this is how you formulate. Now we have not solved it, and I've said earlier that you can solve an LP problem either through using a simplex method or graphical method, and here we are going to use the graphical method. Okay, so we've already formulated. Now let us solve. Now how are you going to solve? First things first is convert the inequalities to equalities and find the divisible of the equalities. Now how do you do this? Very simple. You take these two constraints, x plus y less than equal to 360, convert this to an equality, x plus y is equal to 360. Okay, find the divisible. We'll have to find the what do you call, the coordinates. Okay, because we'll have to plot them on a graph. So x is equal to 360, y is equal to 360, and the other constraint, 2x plus y is equal to 600, x is equal to 600 divided by 2, so that is 300, and y is equal to 600. All right, so there we have the coordinates. Now we have to plot these two inequalities. Okay, plot them on a graph. Okay. If you have a graph paper, if you can get access to a graph paper, you'll get the accurate exact coordinates. Otherwise you can just do this. All right, so this is 0, say 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, 600. Let's stop at 600 because here the max highest value is 600. Okay, same thing with y-axis. 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, 550, 600. So this is your y-axis and your x-axis. All right, now let us plot the coordinates. Okay, now you have here x is 360, y 360. So let us plot for the first constraint. X is 360 and y is also 360. All right. Okay. Now for the next constraint, x is 300, y is 600. X is 300, y is 600. Okay, so there we have it. Okay, x is 300, y is 600. Now this is your x plus y lesser than 360. This is your machine hours M1 hours constraint, and the other one is your 2x plus y lesser than 600. This is your machine 2 hours constraint. All right, now in the maximization problem, here we are maximizing revenue or maximizing profit or maximizing production. We need to find out what is the feasible region. Now this is the feasible region. Now within this feasible region, okay, this is where if you produce, okay, you are going to be able to maximize your profits. Okay, in this this is known as a feasible region, wherein your your decision variables will be optimized. Okay, now let us take the extreme points of the coordinates of this region. You have A, B, this is C and D. All right, now extreme points. So you have extreme points A, B, C and D. Okay, and what are the coordinates in these extreme points or extreme corners? Now for A, of course, it'll be 0 0, right? That's the origin, 0 0. For B, it'll be 300 0. Why? Because value, see, on x-axis it is 300, but y-axis it is 0. And C, now what is C? We have to find out what is C. I think C is for think that will be 240, and this one will be 160. Alright, and for D, now it'll be X will be 0, Y will be 360. Alright, 360. Now what is the objective function? We have to, the objective function is maximize Z is equal to your objective function is what? Maximize Z 2x plus 3y. 2x plus 3y. 2x plus 3y. This is your objective function. Now all you have to do is now substitute these coordinates, okay, and in the objective function. So Z is equal to 2x 0 plus 3y, that is also 0, is equal to 0, right? Now here Z 2 into 300 plus 3 into 0, so 2 3 is a 6, 600 plus 0 is 600. Now here Z is equal to 2 into 240 plus 3 into 160. Okay, so fine, let's find that out. So this is 480 plus 480 equals to how much? So this is 960. Alright, and next one is 2 into 0 plus 3 into 360, which equals to so 1080. Now see, your objective function is to what? Is to maximize, revenue, right? Is to maximize revenue, and you will notice that this revenue is maximized, okay, at which which extreme point? Is it A, B, C, or D? It is D. All right, because this is 1080, the highest. Okay, your revenue is maximized when at this point, this extreme point. Okay, at this extreme point, that means if you produce at this point 0 of X but 360 of Y, you will be able to maximize your revenue. Okay, so since the objective function is to maximize revenue, the firm should produce 0 of product X and 360 of product Y. So that's how you solve this problem. Okay, let's take a look again. The formulation: let X and Y be the two products P1 and P2 respectively, objective function subject to the constraint. So this is the LP model. Okay, and this is how we solve it. We first have to convert the inequalities to equalities, find out the coordinates, plot them on a graph. Okay, find out the coordinates of the extreme points or the extreme corners A, B, C, and D. Substitute the values in the objective function, find out at which point, okay, at which extreme point your objective function is maximized. So it is at this point D, where you produce 0 of x and 360 of y.